Yeah, either if you do it by each figure, or even if you just do each section, because I mean, hopefully each section should have a pretty clear kind of takeaway message. So I guess in the first section we just set up the kind of conceptual basis for why we wrote the review, which is, I guess, I think at the time, and I think it still applies, the sense that the functional connectivity field was quite kind of data-driven, but also kind of maybe not placing enough emphasis on the need for kind of task manipulations, which we couch in this broader framework of kind of, linking these kind of descriptive mappings of these different networks, especially involving resting state, but linking that descriptive insight to something more kind of mechanistic. And I guess in this paper we kind of were maybe a little hesitant to use the word causal, but subsequent to that, Mike's really fleshed that out more. So there's a review paper from our lab that came out a few months ago, Reed et al. It was in Nature Neuroscience, so that also kind of has some extensions of the kind of basic ideas we have here. But yeah, it's about ultimately trying to truly get a causal understanding about how the brain is connected, like different parts of the brain are connected to each other. So this first section, we just describe what we mean by this network mechanism idea. I mean, it's not a new idea, but we just tried to make it more kind of concrete here. So there's a definition in here taken from, I think, Craver's work, who we mention a lot in the paper. But a network mechanism is a set of interactions amongst large-scale neural populations that take part in an explanation of a cognitive process. So the idea is that rather than just, and I guess these first two figures kind of demonstrate that schematically, but rather than the kind of standard way of mapping out just these connections amongst brain regions, it's more about linking them to task manipulations. And I guess a kind of key takeaway of that is there's this ongoing and very productive method development in the field, intersecting with computer science, math, etc., but trying to constrain that with kind of cognitive science approaches. So that's why we have our kind of, this concept of a network mechanism spans these kind of three core components, but the need for a task manipulation or a kind of causal manipulation, more broadly speaking. So you could do a similar thing if you had TMS, for example. So if you stimulated one part of the brain, see how that influences other regions of the brain, for example. But in this case, we mostly prioritize the need for task manipulations. So anyway, so the need for a task is kind of important throughout, but more specifically, we want to understand the kind of spatial topology of these network mechanisms, their temporal dynamics. So like from a task event, when this particular pattern of connectivity emerges, how it changes over time, what kind of time scale it might be operating on. So
what is the difference between fast time scales and slow time scales here?
So, for example, here on the fast time scale, we're looking at like a task-evoked network change. So we have a stimulus that might emerge in an experiment, and then you see this reconfiguration. These regions become connected, and that might switch over time as you transition to another stimulus. So that's fast. That's happening on the order of seconds or milliseconds. Slow is more of like a kind of learning-related, long-term change in the kind of connectivity. So this kind of gets into Hebbian kind of learning ideas. Like, so in this case, we have an initial learning, a kind of network topology that reflects some learning, and then you have an intensive training period over days or weeks, and then you see that reconfiguration happening. So it's just to kind of our attempt to cover as many bases as we can when we're talking about temporal dynamics. And then finally directionality. So we go into this in more detail in that section, but a lot of the field, the resting state functional connectivity field, has been dominated by correlations, which are simple to kind of compute and to kind of understand conceptually, but in a theoretical sense, there are a number of other methods to infer connections that are more sophisticated, and for example, they can tell you whether the influence of one region goes downstream to another one or vice versa. So this idea of adding directionality to your kind of network graph. And this figure is just kind of collapsing across all these concepts. So you might have a cognitive state or a process you manipulated, and this is what the mechanism might look like. So you have a particular spatial configuration. You have a temporal element, right? So like when the task emerges or when a stimulus emerges, then you have this sense of like at a certain period of time this reconfiguration might happen, and also a directional component, so arrows in the graph basically. So that's the concept. The first section goes into quite a bit of detail to try and define this idea, and that leads into the second figure, which is basically trying to convince people that you can have a mechanism at the large scale level of like brain regions interacting with each other, because there's been a historical assumption in the field from a lot of people that to really get at a mechanism you have to look at things that are very fine spatial scale. But what we're actually arguing is there might be meaningful interactions at multiple scales of organization. So that's one thing, and there might be mutual benefits of understanding how brain regions interact with each other to how local circuits and neurons might operate. But there's also a stronger argument that could be made that we kind of touch upon but didn't emphasize it too much because we thought it might be controversial or something, but this idea of emergence.
So what is the goal of this figure?
So this is basically to define this term mechanism, how we're using it in a network sense, and to justify that it's a valid thing. So like you can have a mechanism at a large scale level of regions and networks interacting, whereas this kind of lower portion of this figure is what historically people in neuroscience have talked about as like the only way to get at mechanisms. But we argue that there's multiple scales of organization, and this idea of emergence is that actually a lot of cognitive function might actually emerge at higher levels. So you might only be able to understand it causally if you approach it at the right level of organization. And there's some more detail about all of that kind of the background of that, of how we're proposing that in this section. So that's the first section. It's kind of the basic underpinnings of the framework. Then,
so in first section you want to say about your idea and saying why we are using mechanism in cognitive science.
Yeah, but especially from a network perspective. So the key phrase is network mechanism. Those mechanisms have been proposed most usually at lower levels of spatial organization, so neurons and kind of local circuit populations and things like that. So yeah, it's defining the concept, why it's important, and kind of justifying it with reference to previous kind of...
So what is the one sentence description for mechanism network?
So we have there's a definition on the first page really. we operationally define a network mechanism as a set of interactions amongst large-scale neural populations that take part in an explanation of a cognitive process. So that's the kind of key idea, and then it's more just like, how do we actually empirically find these mechanisms, and that's when we get into it needs to have a spatial component, a temporal component, and a directional component, and then just stating that we can still look at large scale mechanisms. It's valid to do that, and yeah, so that's the main idea. Then it gets more kind of concrete about more like the kind of state of the field, like outstanding questions that we want to resolve by referring to this concept of a network mechanism. So this section here, implications of network mechanisms in advancing human FC research, gives kind of an overview of what the whole paper is going to try to tackle, so it might be worth reading that a bit carefully. So the first empirical section, or one that deals with the empirical findings from previous literature, talks about this need to, so it focuses on the resting state functional connectivity field. And this idea that even though, the canonical networks like the frontoparietal network, default mode network, dorsal attention network, etc., they've been reliably described in different contexts across different labs, but exactly how they relate to kind of cognitive function isn't totally clear. Like there was this in earlier stages of the field, this assumption that when you do this kind of correlation between different regions in the brain at rest, you recover networks that look very much like task activation maps. So the assumption was that this was some kind of Hebbian representation of regions that activate together, tend to connect at rest, like the fluctuations at rest tend to synchronize more. But it's not totally that straightforward. So we talk about this paper that Mike published in 2014, where he showed that if you estimate networks across multiple tasks and at rest, there is a high degree of overlap. So like about 80% of the variance explained in the connectivity matrices, but that still leaves 20% of the variance that is not explained, and it could be that those connections that change between rest and task, even though they're small in number, might be very critical to the emergence of cognition. So this idea that we need to understand this more, not just assume that what we're seeing at rest relates directly to task. And then we get into this, so this idea that there is a stable component of the resting state connectivity architecture that is relatively stable across multiple tasks, and there's a more what's the word that we used? A flexible component, I think that's what we...
Yeah.
A flexible component that changes across tasks. So that's one idea of a kind of tentative mechanism that might explain just how the brain transitions from different states and different tasks. And then we get into this idea to try to formalize that concept more, to try and link resting state FC to kind of task FC and task activations more generally. And then we just summarize Mike's activity flow modeling stuff, which so this in of itself is kind of a network mechanism, because it proposes a model linking resting state FC to the emergence of task activation. So the idea is like the connectivity between two regions, I and J, the strength of that connectivity is going to determine the likelihood of activation from region I flowing to region J. So this it formalizes and tests this idea that the connections between regions are weighting in a kind of Hebbian way the likelihood of activity flowing between them in the brain. And yeah, this figure just summarizes some of the basic results the main results from that paper.
So it means when we have the connectivity in node I, we can predict the node J with the activity flow?
Yeah, pretty much. So this is the basic model. So let's say you want to predict the activation in region J, and you have all these other regions I, separate from J. These red lines represent the resting state functional connectivity, so that could be correlation or regression FC or whatever you want to use. And you make this prediction in J based on the FC between all these regions in J, and also the activation state in those regions I. So it's essentially like a dot product. You so it's kind of it's a simple, computationally simple model, but it makes highly accurate predictions of the actual task activations in these regions. So you might choose one region J, but then you iterate through all available regions you have, and you can generate an activation map for the whole brain. Like a predicted one and an actual one, you can compare them, how much they overlap. So that's the main. From the first section, we need to understand how resting state functional connectivity relates to cognition and cognitive processes during task, and that culminates with activity flow as like a formalized model that can test this idea that resting state FC kind of weights the paths of activity flow in the brain. Then
so this is the network mechanism here, activity flow in resting state.
Yeah, I mean it's a fairly general one. I mean it can just it's aiming to describe just any kind of cognitive task activation, how that emerges. But yeah, it's this idea that rather than just looking at these FC matrices at rest and kind of applying sophisticated, graph theory approaches or ways of summarizing this network and then linking that directly to some insight into cognition, this need to link it to tasks more and actually manipulate and test these ideas more. So then we just get into this idea of network dynamics. So if you go back to the first figure, we're kind of looking now at this kind of how do we get this kind of spatial insight into these mechanisms? How do we get this dynamic temporal insight? So this one deals with dynamics and again somewhat critical of the resting state field because there's been in the last 5 or 10 years a big kind of increase in looking at dynamic FC. So how these matrices change over time. And one big limitation of the field is that again it relies a lot on resting state functional connectivity. So it's been found by a few people, especially in this Lauman paper that we referenced and summarized in some detail, that resting state is particularly prone to artifacts like motion especially, but also heart rate and respiratory, cardiac and respiratory artifacts, because you don't have a task design that you're effectively time locking the brain to, which helps to boost task related, cognitive related signal and suppress motion and other artifacts. So this dynamic FC field, because of its reliance on resting state, this Lauman paper shows quite well that a lot of these these changes in dynamic FC can actually be explained by artifacts like motion. So they show here that head motion artifactually increases FC non-stationarity. Non-stationarity is their measure of dynamic FC, which has been challenged a bit by subsequent papers, but the main idea is that because dynamic FC relies on rest, and rest is kind of task-free, it's not constrained by any kind of task, you have to be extra careful that what you're seeing as these dynamic changes isn't just driven by some artifact. So we talk about that, and then we talk about this paper from Danny Bassett's lab where they combined this kind of dynamic FC analysis. So how does the FC matrix change as you learn a motor task over the course of many weeks? So the same subjects came back, they periodically practiced this motor task, and they were scanned over a 6-week period, and they showed that this kind of increasing kind of modularity in the relevant network. So it starts off as like things are quite connected to everything else, and then over time you get these very kind of like modular constrained network architectures.
So why does it happen during the time? I think the connectivity going to be,
I guess, well, you mean kind of what it might mean cognitively, why it's happening? Well, I guess the idea is like, I'm not sure if it's directly in this paper or in other ones, but
because at the first picture there is no blue.
Sure.
After 2 weeks.
Yeah. So that is kind of what you call a modular organization versus a more kind of distributed, everything's connected to everything else. I mean, I guess it still needs to be clarified exactly what is happening cognitively, but the idea is you're getting better as the task, and this might be a network basis for that process. So like as you become more practiced at something, your architecture becomes more kind of like within network connected. So you kind of, I mean, you could say it's becoming more efficient, but that's kind of speculation. But
so the last one is more efficient?
Well, so because they're practicing the task, that they've become better at the task. So their accuracy improves, their reaction time goes down. I don't know exactly what behavioral measures they used in this paper, but at least accuracy will improve. So that's the idea, is like you're using a task and a task kind of, well, I guess in this case a measure of behavior to supplement these things you're seeing in the networks. So you can't really get this kind of, it's harder to get this kind of understanding from just using resting state, which is again the main idea, is like we need to include tasks more, etc., etc.
And what does the figure B say?
So this is still part of the Laumann paper. This is showing that what is this? So this is showing, I think, that so continuous rest is this blue one, and that has a multivariate. So kurtosis is their measure of like FC dynamics in this paper. So this is showing that like it's kind of providing some hope that there is a real cognitive basis for dynamic FC. So like in this first panel, it's showing that if you more aggressively remove motion influences from your data, you can reduce your kind of FC dynamics you see. So that would suggest that a lot of the dynamics reported in the FC literature are actually artifactual, which is bad. But in this figure, they actually they did all their censoring, and then they still contrasted continuous rest versus these different tasks. And you can see that the mean of the distribution is shifted. So it's showing that as long as you're very careful about how you remove artifacts, and if you have a task manipulation to kind of help make your inferences that this is about like a cognitive process, that real FC dynamics do exist. It's just you have to be very careful about how you infer them. And again, a task manipulation helps.
Mm-hmm. So I understand in terms of network mechanism
Mm-hmm.
in FC dynamics,
Mm-hmm.
it's not enough to just use resting state. It's
Yeah.
better to use task.
Yeah, exactly. Use a task and also be very, very careful about artifacts in your
Mm-hmm.
data because, rest is especially susceptible to them because of that thing of you can't time lock to a task, which in of itself helps boost like task relevant, cognitively relevant signals. So that's the dynamic. Oh yeah, so the last section of this dynamic section talks about how also the field is very reliant on fMRI, despite the fact that fMRI has very poor temporal resolution, so very slow sampling rate, and also the fact that we have the bold response, which is an indirect measure of neural activity. So what we're arguing here is for a greater reliance, a greater inclusion of MEG and EEG approaches, which have a higher temporal resolution, have a more direct measure of neural activity, but with the caveat that there are lots of artifacts that you have to deal with in that data, and also this source modeling problem, which is, so that there's firstly a need to move away from computing connectivity across like the raw scalp sensors, because that's completely spatially ambiguous, right? So then we talk about the need for source modeling, but even on top of source modeling, there's this issue of field spread. So activity from an underlying source will spread to nearby sources as part of this modeling approach.
Mm-hmm.
And there still isn't a totally satisfactory way of dealing with that. We talk about one approach, but yeah, it's just something to be aware of even though we argue for more work being done with EEG and MEG, just we need to also develop ways of dealing with these artifacts. So that's pretty much it for that section. And then this one we talk about kind of adding directionality as a component in these kind of network mechanisms. So I've already gone through this, but like there are problems with correlation. It doesn't convey whether if two regions A and B are connected, whether A influences B or B influences A. There are also other issues with it, which in the Reed et al. Paper that I mentioned, the more recent one, it goes into more detail. So like this idea that you might have three regions A, B, and C, and if A and B are connected to C, then correlation will identify a false connection between A and B. But if you use kind of multivariate approaches like multiple regression, or there's a whole bunch of them out there, you can theoretically get rid of that false connection. But I guess the key point that we make here is that we need to validate these more advanced methods. Like even though they sound better theoretically, they have their own problems. One kind of practical problem often being there's kind of a parameter sweep you have to do. Compared to correlation, which is very simple to compute, there's no real choices for the experimenter to make. But like with a lot of these more advanced methods, you have to choose a threshold or a key parameter, and it's not totally obvious which one to choose. So then we talk about the need to validate both in using kind of simulations of neural data, but also actual empirical data. So we talk about this Steve Smith study that's been cited a lot in 2011, and this Wang paper that kind of extends that. So that's all using kind of artificial neural data. But we reference a paper that me and Mike published in 2016. That is an example of using like actual empirical data to validate these different approaches. So we had the same subjects undergoing fMRI and MEG, the same connectivity approaches applied in both of those modalities, but with an underlying kind of ground truth connectivity change that if a method was valid, it would recover.
Mm-hmm.
And you can look at that paper if you want more details on that, and it's described here as well. But the idea is like we found that a number of directed approaches actually were able to recover that kind of connectivity change that we had embedded using a task paradigm. So again, coming back to one of the central themes of like a task manipulation helping you to make more valid inferences about how the brain's connected. But yeah, I guess the main takeaway from this section is there are a lot of cool methods out there that can add directionality to your kind of connectivity map, but there's also a strong need to validate those approaches for the reasons I've already described.
And I think somewhere you said it's better to use the method that used in history rather than using a novel method.
Right, it's more like don't just use a method because it's new, or don't just publish on it. I mean, rather only if it adds something, it's kind of an obvious point, but a lot of the field, because of this overlap with computer science, engineering, there's been a lot of new methods being written about and kind of added into the literature. But without validation, you could be, it's not necessary just because they're more advanced in a kind of theoretical sense that it'll work with neural data. So yeah, okay, then the final section is more a very general kind of primer on how multivariate pattern analysis approaches might be incorporated into this kind of network mechanism idea. So one reason they might be helpful is because they're more sensitive to detecting neural representations than like standard univariate approaches, like a task GLM or something. But I guess we talk about how you can use these approaches both to clarify spatial components, but also in a temporal way. So there's a very basic summary of MVPA in the field, fMRI and MEG. Right, so in this paragraph we kind of list 3 ways in which MVPA can be used to help us understand network mechanisms. So we can extract higher, like more sensitive spatial components. So for example, there's this method of informational connectivity where you essentially look at how, so like you run this kind of searchlight MVPA analysis. So you have like a searchlight of a certain part of the brain. You extract signal from all voxels within that searchlight, and that gives you a kind of multivariate, like multivoxel space to look at representations linked to a task. And then you cycle through all your regions of interest, and you'll have a kind of a time course of how representations are fluctuating over the course of a task, and then you can correlate that time series across different brain regions. So it's like a different, like at a kind of higher level of abstraction than a standard connectivity analysis, where you would just correlate your time series without linking it to task information directly. So that's one example. Another one is...
So you meant this figure, the figure A, yes?
Yes. Yeah, exactly. So that just talks about the kind of informational connectivity approach. maybe it's easier actually to just summarize this. Then the second way that we can use MVPA is to actually decode cognitive states from the connectivity pattern.
Mm-hmm.
So rather, like what we have here is an activation pattern within a certain region, but we can also like train these classification approaches on connection by connection matrices rather than just activation. And that might have benefits in some.
So what is the difference between TR1, TR2, and
here?
Yeah.
So this idea is that, let's say you have a task of interest,
Mm-hmm.
and let's say TR1 and TR2 is in relation to some onset of a task.
Mm-hmm.
You can compute. Well, there's multiple ways of actually decoding the task information. Like you could train a linear classifier to separate between task A and task B and do that over time. And then you'll have a kind of informational... The idea is that you get from just a raw activity time course
So they're
to an informational time course.
all of them are from one region, but the method is different?
No, all the same method. Let's say you're just using like an SVM classifier, which is a very standard linear classifier. You would then train that classifier to discriminate between two task events, let's say.
Mm-hmm.
And if you did that over time, you would get like a sense of how accurate that classification is over time.
Good.
And then you repeat that for a different region, and rather than then correlating the raw activations time series, you would be correlating their decoding time series with their information time series. So that's the key difference, is like you're projecting the activations into this information space and then looking at how it kind of synchronizes across the brain. So that's one way. Then the second way is just, instead of training a classifier to discriminate task A and task B based on their activation patterns, you would train it to do so on the basis of its connectivity patterns. So there's some examples that we cite that do that. And then the third way, which is actually work that was published in our lab. So Richard, who's a grad student, this is based on his work.
Mm-hmm.
But the idea is that you can actually use multivariate approaches to classify temporal components. So like how the brain might transition from different large-scale states over time. And this whole section summarizes that whole study. It's been a while, so I don't remember it in a lot of detail. But the idea is like in this figure, panels A and B, you're classifying with the aim of identifying spatial components of networks. And this one actually is more concerned about linking that to dynamics. So like you train your classifier to identify these different states, which were linked via a meta-analysis to different cognitive functions.
So what is the green bar?
So this is, if memory serves me correctly, it's been a while. This is, each element in this matrix is the overlap between activation patterns at rest over time. So red means that at time point 50 and time point 48, there was a high degree of overlap in how the entire brain pattern was quite overlapped highly at that time. So you run that for your entire resting state run, and you compute the correlation between activations at each time point, and you get this matrix, and then you apply a clustering algorithm.
So I didn't understand the correlation between resting state and what?
It's all within resting state, but it's like at each time point. So like what we have here is each time point, right? So you can see that there are, as you're nearer in time, you get kind of a high degree of overlaps. So the patterns are more kind of overlapping during then, which is why it's red. But there's also these kind of fluctuations between Yeah, so what the green bar is the result of applying a clustering algorithm to separate this kind of like dynamic FC transitioning matrix into distinct states. And that's what those states look like spatially, and you can see they're quite non-overlapping, and they seem to look a bit like the kind of classic task positive and task negative networks. So this whole section is quite kind of exploratory and just being like, we should use these MVPA approaches that have been applied mostly just in the task domain, so task activations, but using that to further our kind of network insight. So that's pretty much it. And the rest is just a summary of the paper and some kind of things for future research to address. Yeah, and we talk about this need to incorporate stimulation approaches because they're more direct manipulations of like more direct causal interventions into the brain function than even tasks are, right? Because you can literally stimulate one part of the brain, see how that impacts on connectivity and activity in the rest of the brain. And we're actually working on stuff like that now with Travis and with Bart. I guess that's what your project's about, isn't it? Yeah, okay. So that's pretty much it. Hope that helps.
So what is the conclusion of all the paper?
Well, let's read it.
No, not this conclusion. The conclusion that you...
Oh, right. You mean from this?
Yeah. From all of this.
Well, I mean, I wrote it, so I mean, this conclusion is still probably my... Yeah, it's more of like a forward-looking thing. It's like we need to incorporate tasks more. We need to continue to develop new methods that, in the context of a network mechanism, involve spatial, temporal, and directional components, but by use of tasks and also by using stimulation approaches, we need to make sure that we validate those methods for the reasons I already went into, that just because a method is more kind of algorithmically complex, or even if it's just a novel method, it doesn't mean that it will meaningfully improve our kind of cognitive understanding of these networks. Yeah, I think that's pretty much it.
And you said you published a paper after that to extend this work?
Yeah, I mean, I was an author. I was a co-author on it, but I wasn't the first author. But it's... Yeah, it's this one. So Mike's the lead on it, and him and this guy Andy Reid did most of the work on it, but it kind of refines and extends the basic ideas in this paper. So in case you're interested, it's worth reading through. It's a bit long, but it's I don't know, I think it raises a lot of interesting points.
And after I gave this presentation, we should discuss something about this paper. So what's your suggestion?
Which one? For this one?
Yeah.
Oh, I don't know. Do you have to suggest the discussion too? Or will it just emerge from it? Like, from what you've talked about?
No, from the things that I talked about.
Yeah, I don't know, like what I just said, like how do we get a more causal understanding of the brain, how it relates to cognition, but also, I guess more specifically, how the way the brain is connected and how those patterns of connectivity change, how that relates to cognition, versus just a purely data-driven mapping of networks and at rest. All right.
Thank you.